Okay, so from today onwards, we're going to start the class with a CS story. So do you remember yesterday I was talking about Super Mario? So there is a very nice article on Medium that you can read. So someone was asking this question that the entire Super Mario game fits within 40 KB, and the size of this image is 283 kilobytes. So does this make sense? Does it seem logical? What's happening? Any guesses? How is this possible?
The number of bits per sub-image is like very less when it has been done during college.
Right, so are we using the same displays for Super Mario console as opposed to the display on which this image is taken? No, right. So the pixel density is different. That's one of the reasons. Otherwise, it's also a very nice article. So if we discount for that also, but still 40 KBs is absolutely nothing. So the output images were 256 by 240, so the resolution was fairly low. And the final image needed to be displayed was 180 KB. It had only 2 KB of RAM. So just think of it in terms of the systems we use today, the games we use today, the programs we use today. 2 KB is absolutely nothing. The program itself was about from 8K to 1 MB. So memory is comparatively really small compared to the total size of the program. So how do you think it will get executed? So it will be like parts of the program will be run in the memory at a time. Not the entire program can be put in the memory at one time. And for the gaming fellows like who build games, so they're using techniques known as sprite sheets. I guess those who build games would already be aware of this. Quick administrative announcements. So from the next lecture onwards, we'll have a 2 to 3 minute CS story at the start of lecture, which will be given by one of you. So each one gets an opportunity to give this lecture. It could be a technically interesting tidbit, like the Super Mario one which we discussed. It's good that if it's more or less pertinent to the course or the systems we study. Or the other topic you could take is a CS hero, like Grace Hopper or Kernighan, and tell about their contributions, tell about why their presence was really important and how we benefit from it. You could choose either. If you don't do it badly, you get +1. So it's just a +1 over and above 100. The order of this I decided, so I'll run a script which will randomly pick up people from you. You'll have to send in the material, let's say 2 to 3 slides, basic slides in a PowerPoint, just send me the images by 5 in the morning of the lecture. Another thing is that we have a lecture tomorrow, 25th August, 4 p.m. Same classroom. Anyone has conflicts? Works for everyone? So let's meet at 4 p.m. tomorrow then. So we'll also do a very quick revision of what we studied yesterday. Space versus time multiplexing. Space multiplexing, the simplest example is cake, memory. Time multiplexing, the simplest example is classroom, CPU scheduling. We saw direct physical memory multiplexing where we looked up a chip, an actual RAM chip. One of the disadvantages that it's limited to the physical memory. Any other disadvantage of this that we discussed yesterday? Fragmentation. Which are of internal and external. Internal fragmentation is so the space between a single program. External fragmentation is between two programs, and we don't have enough space left. While there might be enough space, but we don't have a continuous block available. There were 3 goals of memory management. Okay, Monica. Any goal of any goal of memory management? Okay, Hardeep. Pranjali, goal of memory management. So just think of what were the goals of CPU management and think the analog is the memory. Transparency. Okay, good. Okay.
Isolating the process.
Efficiency, isolation. The memory interface where we have two types of operations. There is a load, there is a store. And we studied the powerful abstraction. Anyone wants to tell me the powerful abstraction that we studied yesterday for memory management? What is it? So the abstraction. What is the crux of yesterday's lecture? That was virtualization. And what is the what makes virtualization work in this case? What is the problem that this approach had, which virtualization is avoiding? The crux of it. So that's the technical bit. Now, I'm just asking the conceptual bit. So, okay, so let's talk about networking for a second. What is the abstraction that a process has? Let's say I'm running Skype versus I'm running Internet Explorer. Do these need to know whether I'm using Ethernet or Wi-Fi? No. Why doesn't it need to know? Because an abstraction is provided. So you get a layered interface. The higher layers don't need to bother about the load interface, and there is a decoupling. So the physical layer, the physical medium, could be anything. Similarly, in the case of memory management, the main abstraction is that the addresses on the physical memory or on the RAM chip do not have to be the same as the addresses that the process is using. So this is the concept that we need to grab, and we'll keep on looking at similar. So if we get this, we get the crux of this, we'll be like we can see similar abstractions in other fields of CS. Yeah. So the abstraction is to decouple the physical memory and address. Okay. So someone yesterday had doubt about assembly language and what are the instructions being used. So in the book, oftentimes we are in the due course of lectures, we are sometimes looking at assembly and some of the assembly instructions. So I wanted to walk through a very simple example. We'll not go into the super details. We'll see a very simple example to get us enough of understanding of assembly language. So we saw this code yesterday. There is a compiler which will create this kind of an assembly. And so this goes into the program code. There's an address which is being read for reference memory reference. But let's look at something even simpler. So here is a simple hello world program. It sets x equal to 10, increments x by 4, multiplies x by 4, returns 0. Pretty simple program. So I've compiled it and I've used OTool, which is a disassembler. You could also use, there is something similar in Linux which you could use. So you disassemble it and let's see the different parts of the assembly code being generated. So these are different registers, RBP, RSP. Anyone remembers what RBP would be? Forget R for now. What do you think BP would stand for? Base pointer? SP? Stack pointer? AX? Okay, so let's not look into all the details. So this is something you can study on your own, but let's look at some of the important things. So all of these, if you remember, if you see that there is Q, L at the end of these. Anyone remembers what these could mean? Any guesses? L could be, yes, L could be long, Q could be. So L stands for long, Q stands for quad-word. These are basically the sizes of the. So we have move, XOR, add, shift left, pop, return. Let's try and find out where this operation is happening. Int x equal to 10. So we have a base pointer. So there is a push operation. So maybe it's pushed onto the stack. Something of that kind is happening. We have, so we move 0 into RBP minus 4. So basically the base pointer and the address which is 4 bytes below this, we move 0. So where are we using 0 here? Sorry? So one is return 0. Is there any other place we could use 0? So this is my guess that when they're creating index, it means that they're creating, like they're pushing 0 to the variable. I don't know if this is correct or not, but this is my hunch. So next, what happens is you move 0xa. So 0xa is what in decimal? 10. You see 10 here? So you're moving 10 to RBP minus 8. Okay, so next you have another register, ECX. You're moving the content of RBP minus 8. So what was RBP minus 8? What value does it contain? It contains the value of x, which is 10 in this case. You add x4. x4 is decimal 4. So you add to it. So now ECX becomes x plus 4. X has not yet become x plus 4. ECX has become x plus 4. Then you move the content of ECX to RBP minus 8. So RBP minus 8 is a reference for x. So now x becomes x plus 4. This is the interesting bit. So these are some of the optimizations which the compiler makes. So we're doing shift left of 2 on ECX. Why do you think that we're doing that? So multiply by 4 can be written as shift left of 2 times, right? Why do you think the compiler is doing this? Over adding 4. Like you could have added, you could have multiplied by 4, but you could have shifted left. Why do you think the compiler would have done this? Faster. So it requires maybe lesser amount, there is lesser overhead, it's faster. You've shifted left, and then you again move ECX back to RBP minus 8. So ECX was this computation. ECX was basically RBP minus 8, shift left 2, and then you multiply, then you move it back to RBP minus 8. So you again get the value of x equal to x into 4. You pop RBP from the queue. Now where is return 0 happening? Or where else do we see 0 in this assembly code? Okay, so whoever finds this again gets a +1. The first one to find this.
Pop Q of RBP.
Pop Q doesn't contain 0.
RBP contains
Sorry. So where is 0?
-4.
It's
RBP -4.
Sorry?
a quad word, so RBP currently point to 8. So when you pop it, it's get decremented, and then returning that will. Returning is usually from a fixed point, usually at the start, so 0 is the value is stored there.
I don't think any of you thus far given the right answer. And the way I verified this was, instead of writing this program, I wrote another program which returned 1. So let me do that, and then let's see who gets now a plus 0.5. So you don't get a +1 now. This is how Hello World 2 looks. So you see that it's mostly the same, the only difference being that I'm returning 1 instead of returning 0. And I've compiled it. Do you see any difference now? Third line is you move 0x1 to EAX. So previously you were doing XOR of EAX with EAX. If you do an XOR of 2 with 2, you get 1 with 1, you get 0. X with X, you get 0. So that's a very efficient way of getting 0. In the other example, you're moving it. So move is more expensive compared to XOR. These are some of the tricks which the compiler, the assembler will carry out.
What does EX stand for?
It's one of the registers. So again, I'm not an expert on assembly. I just started this just to give you enough background on what's happening. So what does RBP minus 8 means? And in this convention, so there are 2 different conventions of assembly. In the convention, we're using percentages. So you move from the source comes first and the destination comes second. So move L from 0 to this means you move this content into this app. There is another convention where you do the reverse. So the order is reverse. Okay, a very quick revision on general address translation. We have a CPU which, let's say, which is executing some instructions. The virtual address required is hex 10102030. It goes to the MMU, it goes to the kernel returns something. In this case, let's say it returns a physical address, which has changed. So if you noted, it's not the same as yesterday. Then you can request this address from the physical memory. What if you want to transfer the same virtual address again? Smith, what do we do? So this is a meta cache. So I asked you the same question yesterday.
Okay, what if you want to transfer this?
So I want to ask the MMU for the same address again.
First to the cache, then to
Cache. So the cache is going to respond with this answer. If there is a context switch, the cache has to be removed. One of the ways to do is to empty the cache. Okay, let's begin relocation, which is based on bounds based approach. So we have a virtual address. It's a 0x100. It goes to the MMU, it goes to the kernel gives back something. It gives you now two set of registers. One is the base, one is the bounds. Any ideas on what base and bounds could be? So we need to do some address translation. What would happen is that a block of virtual address would correspond to a block of contiguous memory on physical memory. So what could a base and bound be? So start of
Physical.
start of block on the physical memory. Bounds is size of on. The size is going to be the same on both, on virtual as well as because it's a contiguous, equally spaced, equally sized memory. So very simple two set of registers. The physical address would be the base address plus the virtual address. So assuming that virtual address starts from 0x000. Okay, everyone gets that? Physical address is base plus the virtual address.
So this is the bound for the address space.
This is a bound for the address space of this process. So another way to look at it, as I was suggesting earlier, so you have a block here, you have a corresponding block here. So as long as you get this mapping correct in your brain, the block here corresponds to an equally sized block here, just that the start and end are different. So if you just know the start, you're effectively done because you know the size here remains the constant, so you just need to map out the starts. This is the base register. Okay, when do you think the base and the bounds register will be set up? Start off.
Process.
Why not start off the OS?
Because then process is not existing.
So this is done on a per process basis. So there are a bunch of things which we store for a process. This is one of them. What happens if context is switched?
New cache.
Sorry?
Switch the cache.
So if the context is switched, firstly the cache has to be emptied if you're maintaining a cache. But for now, let's forget about the cache. So the base and the bound registered will have to be stored somewhere. Whichever process now comes into action, let's say process B comes into action, we need to load its base and bounds. So who is doing these operations? The kernel is doing these operations, and that is why the MMU interfaces with the kernel. And that's why it's not an independent entity which can give you the direct addresses. So we have base and bound registers. This allows us to place the address anywhere in memory. So the virtual address, let's say, starts from 0 to 16 KB, but the physical address could be from anywhere, which is now given by the base plus base from base till base plus bounds. So that's the address in the physical memory. It also ensures that process is only accessing its own space, given that you have a bound register. So we'll come back to this in a minute. We have this simple formula now. Physical address equal to virtual address plus base. This is assuming that the virtual address space starts from 0. If it were not starting from 0, how will this formula change? So you'll have to then subtract the start address from the... so you'll then have VA minus VA start, something on that lines. So let's look at an example now. So we have from 32 KB to 48 KB, this is the entire physical memory is allotted to this process. So this is how relocation was happening. We had this process This is from 0 to 16 KB on the virtual address space, but on the physical address space, it's from 32 to 48 KB. It's called relocated because it's now been relocated to a different physical address space. Okay, so the OS has this job to decide where in the physical address space to load the address space of the process. How do you think the OS would go about doing this? Okay, if you are the OS, you are given this physical address space, and you have to load another process. What will you do?
You will like load wherever it's free in the top.
Wherever it's free, wherever it can still accommodate my requirements. So let's say if it's another 16 KB process, you could either store it here or there, and depending on the order in which you're scanning, you can store it anywhere. So in this example, the base is, what's the base register value? 32K. The bound is
16.
Okay, so let's go back to the example again. So we had, so by the example I mean the compilation example that we started yesterday. This particular example. So we have move L0x0 to EAX, so we're moving the content of EBX to EX. At this point of time, the program counter is pointing to address 128. The fetch instruction will get executed. We calculate, so for each 128 here is a, what kind of address? Virtual address. So for each virtual address, we'll have to calculate the corresponding physical address. In this case, corresponding to 128, we have the base of 32K. The virtual address is 128. So the physical address generated is 32896. But this is what happens for each and every instruction. You get the virtual address, you send it to the MMU to get back the physical address. So this is another way to understand this. So if you want the systems to grow quicker, like if you want the CPU execution to become quicker, one of the ways is to get a better CPU. The other is to get a quicker MMU or RAM. So MMU also has to become quicker in order to translate this quicker. So after this, once you fetch the instruction, you'll execute this instruction. So one of the instructions in this particular example was where the data was residing in virtual address 15 KB. So you fetch the data from the actual physical address and not the 15 KB virtual address. So this is 32 KB plus 15 KB equal to 47 KB. Okay, so why is this concept also called dynamic relocation? So base and bounds approach, this whole paradigm is also called dynamic relocation. Any guesses why?
Because not every time that it will be relocated at the same location.
Okay, that's very good point. Excellent. Any other thoughts?
So while compiling it, you don't have to worry about where it is going to be stored.
Excellent. So if it was static relocation, you would then use compiler then the compiler would give you the exact physical addresses, which is not good. So dynamic, every different run of the compilation or every different, every single run when the process is loaded into the memory could have a different address space, physical address mapping. Any other reasons of this dynamicity? So could you, let's say if I want to do defragmentation, what will I do?
You'll move the physical address space.
So defragmentation means that we move the physical address spaces in a way that there is more of contiguous space available. So one other aspect of dynamicity in this case is you have an address space, but let's say you have a lot more processes waiting in the queue which require more contiguous space. You do defragmentation, you move this entire physical block somewhere else. So that's also the dynamic nature. The program will run transparently. So that's, again, one of the goals of memory management. The program has no clue what's happened with it. Next time the instruction executes, it will go to the new address space, physical address space, without being affected. So we can change the address even after creation. Why would you do that? For one of the reasons could be for defragmentation. Okay, so we also looked at the bounds register. And once we, couple of slides back, we were looking at goals of OS for memory virtualization. So we mentioned this goal of protection or isolation. So we want to protect processes from each other. So this is done via the bounds register. The bounds register, as the term, like as you would have already guessed, checks if the memory references are within a specific bound or not. What will happen if they're not? So you'll have segmentation fault, you'll have some other kind of fault. What was the bound in the example we were looking at? 16 maybe, right? And if you have an incorrect virtual address, so by incorrect virtual address, I mean that it's out of bounds, you get the process is terminated. So let's work out some simple examples. Let's say we have a virtual address. Unfortunately, I didn't. This was supposed to be an animation and was supposed to come later, but you can close your eyes or don't selectively focus on the other parts of the slide. So a virtual address 0x100 goes to the MMU, it goes to the kernel, you get back the base and the bounds register if it's already not in the cache. So you start with 1000, you add 0x00, you get this particular address, which is 0x100 plus 0 plus 0x0100. And this could have gone up till 0x300. Let's look at the second example. Again, continuation of the previous one, 0x200. Pretty simple, right? You get 0x100 plus 0x200. So I would always visualize these. So I would always tend to draw these in terms of the exact mappings. In terms of the scale, that always makes it easier for me to understand. What if you have 0x400? Is it in bound? In the bounds, no, because the bounds was 0x300. Another way to look at it, so the bounds should have finished there, but it's gone beyond that. So this memory is not allowed to access, so you get it's not allowed. And you get a segmentation fault. So there are few set of hardware requirements for dynamic relocation. So you require a privileged mode. So where were we using a privileged mode previously? So whenever we want to execute some kernel level operations, and you want to prevent user mode from privileged operations, why are we using the base and the bounds register? So you need a pair of registers to support the address translation and the bounds. Right? You need to have, the hardware needs to have an ability to translate virtual addresses and check within the bounds. So for that we require some circuitry. So all of this simple addition would require some circuitry. So if you've studied some basic architecture, you would have studied some adders and some other simple circuitry. Privilege instructions to update base and bounds. You need that because the OS has to be able to set these on a context switch or setting up a process. Privilege instruction to register exceptional handlers. When would an exception occur? Whenever there is out of bounds or something incorrect is being done. Ability to raise exceptions when you're trying to access privilege instruction or out of bound memory. Now, so this was the responsibilities. These are the responsibilities of the hardware for dynamic relocation. What do you think are the responsibilities for the OS? What does the OS need to do? So we've already discussed that. We're just summarizing it here.
Context switch.
So one of them is context switches. Definitely one of them. In terms of just in listing them out, so we have memory management. So every time a new process is created, the OS has to allocate memory for the new process. Whenever a process terminates, the OS has to reclaim the memory back. And what does it do in the free time? So what does it do in the other time when it's not either allocating or reclaiming memory? Could it defragment? Could it reorganize? Could it maintain a list? So it also has to maintain an operation. It also has to have an operational list of all the freely available addresses in the physical space. So this is another responsibility which the OS has. It has to manage the base and the bound registers So it has to set them upon context switch, which also means that it has to store and restore. Restore for the incoming process, store for the outgoing process. The OS has to have the capabilities of raising exceptions, which means that whenever a out of bounds call is made, so it terminates the offending process. Okay, what do you think would be some of the advantages of base and bounds? Why should we use this?
Easy conversion of virtual address to
Easy. So one general trick in many of the questions, even in the programming questions or interviews that you'll see, is the pros of the first approach. So this is generally true. So whenever you come up with the first approach, one of the pros you can always remember it. That's easy to do. So that has a corresponding con also, which so it's simple in terms of the fact that the hardware only needs to have 2 registers. You just need to know the base and the bounds. And it's also going to be relatively fast. Why is it fast? What are the operations being done? So one is a comparison for checking the bounds. The other is a simple addition for translation of the address. Okay, cons.
heavy internal fragmentation.
Sorry?
Heavy internal fragmentation.
Heavy internal fragmentation. Could you explain how?
So when we set the base and bound, the program itself might not need that much amount of space per second.
Right.
So the OS is almost always allocating what the program is asking.
Excellent. So we saw the address space as different components. One of them was code, heap, and stack. Heap and stack have a lot of gap between them, but the major con of base and bounds is that if you have X amount of bytes or kilobytes in the virtual address, so you have to give the same contiguous block in the physical address. So contiguous blocks are always bad for large contiguous blocks are always bad for fragmentation purposes. So we have base plus bounds. This is the exact replica, but it's just relocated of the virtual address space. Whenever you require contiguous block of memory in the physical memory, you have internal fragmentation, as Tom will say, which also then can lead to external defragmentation because whenever you end up using larger blocks, you're left with a relatively less number of smaller blocks available. Okay, so we'll now start the second approach, which is an improvement over the first approach. Okay, have we studied segmentation before in architecture? So when we hear about segmentation, what's the first thing which comes in our mind?
Makes more segments of the.
No, that's so you're telling the answer. I'm asking you if you've not attended the OS class and you're a C program, where do you hear segmentation? Segment fault, right? So now we'll quickly see that what segment fault could mean. So we have code, heap, stack. These are different parts of the virtual and the physical address space. So segmentation is a very simple idea that instead of having a simple base and bounds register for the entire address space, now we have a base and bounds for each of these segments. We have a code segment, we have a heap segment, and we have a stack segment. So we have a base for code, base plus bound for code. And I love that Keynote has this animation of line. You have base for heap, base plus bound for heap. And similarly, you have base for stack and base plus bound for stack. If you notice, there is something different in stack compared to the other ones. What is the difference? So all of them are growing downwards in increasing order of physical memory and virtual memory, but stack is growing in the opposite direction. So the base will be the bottommost address, and the base plus bound is like an offset in the positive, in a lesser address space. So segmentation is similar, but different in the sense that instead of having a single base and bound per process, now how many base and bound registers do we need to store? Why 6? How many pairs of base and bound do we need? 3 pairs or the number of segments. So in this particular example, we had 3 segments. if we have X segments, so we have 2x the number of registers or X number of pairs of base and bounds. Each base and bound corresponds to a segment. The another big advantage of segmentation is that so each segment can now have its own size. So we're not so in the previous case we just gave an entire block of address using base and bounds. Here we can have different. Each segment can have its own size, and more importantly, each of them can have their own permissions. So any example why you'd want different permissions for different segments? Okay, so we have 3 segments: code, heap, stack. Why would we, any example where we could have different permissions for these?
You won't need to store into code.
Sorry?
You don't need to store into code.
You don't need to?
Code is not altered.
So that's an excellent point. So code is not altered. So what kind of, so if you cannot alter something, or if you don't want to alter something, what is the permission mode called? Read. So it's read only, and maybe execute only because you also want to execute the code. So it's usually beneficial. So now you have tighter constraints on the address space. So we'll also look at another example if we have time today, otherwise in the next lecture, why this can be beneficial for saving memory. So let's talk about it right now. So let's say we have process A, and we have 2 instances of it running. So could we save some memory now? The code can be, because the code is unmodified, it cannot be modified. Can we maintain a single physical segment for the code and give it to both the processes? Does it make sense? Anyone not with me? Code in this case is a read-only segment. Each segment can have its own direction of growth also. Now we can have a stack going upwards, the others going downwards. So here's a TLDR version or mini guide to segmentation. So if you don't understand anything in segmentation, just look at this slide, and hopefully you should just revise this before the exam. So each segment has what? It has a start virtual address. It has a base physical address, and it has a bound. So what's the difference between segmentation and base and bounds in terms of each segment?
The start virtual addresses.
So in base and bounds, we didn't have a start virtual address. In fact, we had, but by convention, we set it to 0. So we could have also altered the base and bounds to equal to start virtual address, but it didn't make sense. So why do you think each segment has a different virtual address?
Different parts. Code parts.
So let's say we have 3 different parts of the code. Now the code wants to write something on the stack. So they must maintain some relative ordering. So you cannot start each of them from 0 to 2 KB or something on that lines. So each of them get an absolute kind of an address in the virtual address space. So that is why for each of them we need to store the start virtual address. How do we check? How do we check if a virtual address is okay or not? So the first thing you'll want to do is to check which segment the virtual address belongs to, and then for that segment you check whether the virtual address lies within the start of the segment to the segment start plus segment bound. Is this clear? Is this simple check clear to us? And for translate, what do you think we'll do then? What do you think will be the formula?
Physical address equal to virtual address minus the start plus base.
Okay, that's perfect. Physical address is equal to virtual address. So let's say we have some virtual address. It belongs to segment start plus segment bound. It is somewhere in there. We subtract the segment start from the virtual address. Now segment start corresponds to segment base. So segment start plus segment base, and you subtract this from. Simple formula. If you still don't get it, I'd suggest drawing these things out. That usually makes it very clear. So let's take an example of segmentation now. Let's say we start with virtual address 0x100. What happens next?
segment.
So it goes to the MMU, which then goes to, which will come back with.
The segment and
So it will come with three things now: base, bounds, and so the kernel will look at the virtual address. It will see whether this belongs to some segment or not. If it doesn't belong to any segment, then the kernel will say that it does not belong to, and you'll get a segmentation fault. But if it belongs to some segment, you will be returned that particular segment set of registers. You will be returned the start, virtual address start, the base, and the bound. So let's say this particular virtual address comes from the code segment of the data, and let's say the code segment starts at address 0, virtual address 0. The base address is 1000, hex 1000, and the bounds is 300, hex 300. So the virtual address can go from 0 to 300, hex 300, right? Because that's the bound. So the bound is going to be the same across both the physical and the virtual address space. Virtual address 0 corresponds to what physical address?
1000.
Virtual address 300 corresponds to what physical address? So 1000 plus 300. So again, we draw this picture. So as I've been saying aloud, so this at least helps me. I think this will help all of you if you just keep on drawing these schematics, simple illustrations. So this particular segment, let's say the code segment, is relocated in this part of the physical memory from 0x100 to 0x100 plus 0x300. So we had two kinds of processes or two kinds of steps to do. The first was check. So there'll be a check which does that segment start is less than virtual address, is less than segment start plus segment bound. The segment start is 0x000. The segment bound is 0x300. Does 0x100 lie between them? Right? So it's thumbs up. You can proceed further. The second part is, so once you've done a check, you do a translation. The translation formula is virtual address minus the segment start plus the segment base. So if you look at it, so we started this process, the segment started, in this case, virtual address started 0x00, so it's 100 offset from there. This starts from 0x100, so that's 200 offset from here. So you get a simple one-to-one mapping. 0x100 minus the segment start, 0x000, plus the segment base, 0x100. Clear to everyone till this point of time? And then you go to that particular location, you get that access. Okay, 0x2400. What happens? Someone tell me. Anyone? You go to the MMU, kernel comes back. Does it come back with the same base bounds virtual address register? No, right? Why?
It is outside the zero.
Because 2400 is outside the bounds of the previous one. If it were within the bounds, so we could have equally well used the cache or some kind of mechanism similar to that. But now we'll have to again get a new base and bounds register for this particular segment. Starts at hex 2000, base is hex 3000, and bounds is hex 600. So what's the total address, start address and end address in the physical memory? 3000 to 3000 plus, and the virtual space 2000 to 2000 plus 600. So again, you see a one-to-one mapping, fairly simple. So it goes from 3000 to 3000 plus 600. You first do a check where the segment start is less than virtual address is less than segment start for segment bound. That holds true because 2000 is less than 2400 is less than 2400 plus 600. You do a translation, which is should be 3000 plus. Sorry, what are you saying?
2000 plus 2000.
Segment start plus, yeah, sorry, that should have been 2000 plus 600. The physical address would be the base address plus virtual address minus VS star. So 3000 plus 2400 minus 2000. Now let's pick up virtual address 0x2700. We go to the MMU, goes to the kernel. We see that there is no process. Sorry, there is no base and bounds corresponding to this. If we have, so we had two base and bounds registers. One of them was 0x000 base, so it starts at 0, ends at 300. The other one starts at 2000, ends at 2000 plus 600. Now it's outside of both of these. And there exists, let's say, no other code segment for which we have the base bound on the start address. So what will happen now? What will the MMU return? We do the check and we get a segmentation fault now. Okay, so how do we get which segment is running? Or which segments registers should we load? How do we think that, how would you think it would be done efficiently in the OS? Sorry? So everything is, let's say we start with this example. Now, this is the example produced in the book. And the mechanism written here, like what we'll be studying, will hold for this example. It may or may not hold for all the examples. That's at least what I think based on what I was working on. So you start with the virtual address space. The first 2 kilobytes are program code, 4 to 6 KB is heap, 14 to 16 KB is the stack. So the stack, and this I've actually written as 16 KB minus 1. So 16 KB minus 1 you can represent in 14 bits as the following. Does everyone remember binary conversion? So a single byte 1 is 1, 1 0 is 2, 1 0 0 is. So if you have 1 at the nth bit and you have zeros everywhere else, so what's that number? 2 to the power n minus 1. So this has 14 bits. 14 bits, all of them set to 1. What's the next number? 15th bit is set to 1. The remaining bits are 0. That number is 2 to the power 15 minus 1 to the power 14. That number is 16k. This is 1 less than 16k. So in the book, they have mentioned 16k, but I think this should be 16k minus 1 for the example to work. The first code, first base is 0 KB, which is all zeros, 14 bits. The program code ends at this 2 kilobytes, which is 0 triple 1, 4 ones, 4 ones again. Heap starts at 4 KB. So for all of these, if you're getting confused, just do 4 into 1 or 2 4s. So 1024 is 2 raised to power 10. So if you don't even remember that, like if you have a hard time remembering that, 1024 is the square of 32. 32 is 2 raised to power. So 2 raised to power 5 is 32. 2 raised to power 10 would be 2 raised to power 5 squared. 1024. You move 2 more bits, so you get 2 raised to power 12. And that's how you can easily remember some of these tricks to get the binary conversions. 6 KB, so it's 6 KB is 2 KB plus this. So again, you can calculate 2 KB. 2 KB is 2 into 1024.
I wish I could help, but you don't seem to be connected to the internet.
Why? This was put on flight mode. Okay, so 6 KB is this particular binary address, and 14 KB is 1 1 1 2 0 4 zeros and 4 zeros. So again, if you're not familiar with this, just work them out, and just verify them using a scientific calculator. Yeah. 2 KB. Where you calculate? So 2 KB. Okay, so 2 KB is 2 into 1 0. So this should be 2 KB minus 1, I think. Yeah, so I've generally modified some minor things from the example showed in the book, and there's a reason behind that. So if we just use 16 KB, what would be these two values? So these two would be 0, all of these would be 0. We have an additional bit, which would be the 15 bit, which would be set to 1, right? So we'll now see why this 1, 1 was important for us. So now we're trying to identify the different segments. Can you notice something in the program code? What are the first 2 bits? In the heap, in the stack. So if this was actually 16 KB, this would be 0, 0 is the same as this 0. So that it would have created confusion, right? So I think the example does not directly map to, and that's why I had to do some other small bit of manipulations. So we have 3 different segments. How can you represent 3 numbers? Using how many bits do you need to represent 3 different numbers? 2 bits, right? So using 2 bits, you could have represented 4 different discrete cases, but we here have 3 cases: 0, 0, 0, 1, 1, 1. We could have had something in between that would have been 1, 1, 0, right? So that's another way to look at it. So that's why you're looking at the topmost 2 bits. If it were 5 different segments, how many bits would you use?
3.
First 3 bits, right? So the first most significant 2 bits give us the segment of the code, and we can write a very simple formula for this. So how do you efficiently get these bits? So we saw in the assembly line, in the assembler program. So when assembly code is written, shifts are much more convenient or quicker compared to direct multiplication, subtraction, or those kind of operations. So, and binary operations such as binary AND or binary OR, so they are also very efficient. So in order to get these bits, can we do something like do an AND with 1, 1, and you can basically put all of that to 0 also, you don't even care about that. But the first 2 bits need to be 1, 1. So if you do an AND of 1, 1 with 0, 0, you get 0, 0. You do an AND, binary AND of 0, 1 with 1, 1, you get 0, 1. You do an AND of 1, 1 with 1, 1, you get 1, 1. So you do a virtual address. These all are virtual addresses. So you do a virtual address times with AND with a segment mask, and then you do a segment shift. So how many bits do you think we need to shift here? So basically we want these two to come here to the rightmost location. 12. So the segment mask becomes 1, 1, all the other things is 0. Actually we don't care about them. And then we right shift them by 12 places.
So if we shift directly also,
Directly
like without and doing and mask also, then it will be like that.
you do direct.
Like we don't care about the last bits in the
That's true. So one of the things particular, this is somewhat peculiar because you generally don't have 14-bit address spaces. So you also would have probably do a 0, 0, and you would have probably, let's say, 16 bits. So then you do an AND with 0, 0, 1, 1, and these 12 bits, and then you do a write. But there could be other ways of doing this. So let's take an example. Let's say we pick up a segment in the program code. Sorry, we pick up something in the program segment, which is virtual address 00, 40, 40, 10, 10. What is this number 1010?
10.
10, right? And 10 lies between 0 and 2 KB. Is that right?
Yes.
2 KB is 2048, right? So we need to first find the segment corresponding to this. So we want to ensure that this belongs. We need to somehow show that this belongs to the program code segment. We have 11 0 0 0 0 0. We do a binary AND with this. What do we get? We get 0 0 0 because AND of 1 and 0 is 0, 1 and 0 is 0. You right shift them to 12 places. You get these 2 bits now. Based on these 2 bits, if these are 0 0, you say that it's program code. If it's 0 1, you say it's heap. 1 1, you say it's stack. Fairly simple calculation. So this then says that the segment is the code segment. Let's pick up something from the heap. 0, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0. We do an AND with 1, 1, 4 zeros, 4 zeros, 4 zeros. AND of 1 and 1 is 0 and 1 is 0. So you get 0, 1. By accepted well places, you get the least two significant bits as 0, 1. And these then tell that corresponding to 0, 1 least two significant bits, the address is from which segment? Heap. Okay, so the second part of this is to find out the offset. So we have the first two significant bits which tell us the segment, and then how much into the segment is this particular address. That's called the offset, and we'll study that in the next lecture. So see you tomorrow at 4 p.m. in this.
So why are we ANDing?
Sorry?
Why are we doing the AND part?
So AND is